The last part of this chapter involves inverse trig functions. These are not the same as reciprocal trig functions, sec, cosec, and cot. The inverse trig functions are inverse functions of sine, cos, and tan. So these should do the exact opposite of whatever sine does to a number. If you put 30 degrees into the calculator and you do sine of that value, it gives you a number, a half. If you then do inverse sine of a half, you get back the 30 degrees. So we're going to think about what is going on mathematically with those inverse sine, inverse cos, and inverse tan functions. So start with this exercise. I'm thinking of an angle. I plug it into the calculator, I do sine of my angle, and I get an answer of a half. What do you think my angle would have been? And when you've got a number that you think, are you sure? Can you be sure? Can you know for certain what that number would be? And if not, why not? This is the essence of why the inverse trig functions are a little bit tricky or potentially problematic. They're going to spoil some of the nice rules that we've got about inverse functions, unless we're careful with them. Let's investigate. Clearly something is happening with inverse trig functions, so have a go at calculating some of these. You can pause the video and try working these out. What I want you to be looking for is what kind of answers you get, how they correspond to the numbers you put in, and then when you've tried looking at some of those, do a bit of an investigation, see if you can get a sense of what kind of numbers come out from inverse sine. Are there some numbers that you never get? Is there a range within which you can get values and other numbers that you can't ever get out of inverse sine or inverse cos or inverse tan? So here's the main issue we have. Sine x is a many-to-one function. You can put a wide range of different values into it and still get the same output. We can do sine 30, sine 150, sine of minus 330. You can add 360 or take 360 from any of those values as many times as you like. You'll get even more numbers, all of which, if you do sine of them, give you an answer of a half. So we learned when we looked at functions, you can't find an inverse of a many-to-one function. A function, to be a function, needs to have one single unique output. So sine works fine as a function, but because it's many-to-one, if you try reversing it, what you get is a one-to-many mapping. And if it's a something to many, it can't be a valid function. The calculator can't give me a list of all the possible answers, in the same way that it can't give me the list of all possible answers to the square root of 9, in a sense. If you square a number and get an answer of 9, there are multiple different possible numbers you could have squared. And yet that doesn't stop the calculator from doing the square root of 9. So we want to be able to reverse sine x, and we already have a way of reversing things like x squared, which is also a many-to-one function. 3 squared and negative 3 squared are two different values that give the same output. So what is it about the square root function that allows us to do this? Well, we can get a good idea if you try graphing them both. What I've got here is y equals x squared. That's shown in the middle. You've got half of it dotted for reasons that become clear. And we've got y equals the square root of x. This one is the red graph. And if you look closely, you'll notice hopefully a couple of things. One of them is the red graph is a reflection in the line y equals x from one branch of the y equals x squared graph. That is because it is designed to reverse the process that y equals x squared applies. When you put 2 into y equals x squared, you get 4. We want to be able to put 4 into y equals root x and get 2. In other words, it's the same mapping fundamentally, but going backwards. We need the inputs to become outputs and the outputs to become inputs. And since the input is represented on a graph by x and the output by y, creating an inverse function is essentially the same as reflecting a graph in the line y equals x, swapping the x and y values. If the point 24 is on the original graph, then the point 42 will be on the inverse function graph. The second thing hopefully you've noticed is that only one of the branches of y equals x squared has been reflected. The other one, well, we can see where it would go, and you could even draw it on. And in fact, if you ask GeoGebra to draw you something like y squared equals x, then it will draw you this, an exact reflection. We'll look at parabolas that you can define like this next year, but they're not functions. Just like a circle is not a function. It's a perfectly valid graph to draw perhaps, but it's not a function. So when we're looking at this, we need to remember that this works fine, but there is a restriction that's taken place. This is the restriction that's happened. The graph we're looking at, that's in bold in black, is y equals x squared provided x is greater than or equal to 0. By restricting the domain of the original function, we can turn what was normally a many-to-one function into a one-to-one function. Essentially, we're pretending to the calculator that the only time we ever square anything, it's a non-negative number. So it can safely reverse the process for us and tell us what it was we squared. We know that the value we could have squared might have been positive or negative, and we use our common sense to adjust for it. If the calculator tells me confidently that the reverse of squaring something, having got an answer of 4, what did I square? The calculator will tell me 2, but I know that it could also be negative 2. We do the same thing with inverse sine. The calculator tells you the inverse sine of a half is 30, and then you use common sense and the graph and the symmetry and a unit circle to calculate various other values that would also work. We have a principal value for trig functions, just like we have a principal square root, the positive square root. So what I'd like you to do now, pause the video and sketch 3 standard trig graphs, sine, cos and tan, and mark the key points in radians. Make sure your graphs go forwards as well as backwards, or backwards as well as forwards, from minus 2 pi all the way up to 2 pi this time. That will become relevant in a moment. We're going to find a way to restrict those graphs so that we turn them from many-to-one functions into one-to-one functions. We're going to go through now the process of restricting the y equals sine x graph in order to generate the inverse y equals sine to the minus 1 x, or sometimes called arcsin x. When I've done this with this slide, I encourage you to pause the video and have a go doing the same process for yourself with cos and tan, and then I will show you the results on the screen afterwards. So to start with, we need to think about which bits of this graph we would definitely like to keep. We're going to have to throw away some bits because there are repeats. We can't, for instance, have this bit down here and at the same time this bit over here, because if we try doing inverse sine of minus 1, we don't want to get 2 different answers. It would be nice to get an answer, but we shouldn't have 2 different answers. The most sensible place to start is in the middle. We would like to include the point 0. We want to have sine of 0 equals 0 and inverse sine of 0 equals 0. And if we're starting in the middle, then we want to be able to move from the middle. We want to have a range which is continuous, doesn't have any jumps or gaps in it. So we'll start with the acute angles. If we go from 0 to pi by 2, everything's fine. The graph is continually increasing within the range 0 to pi by 2. And that means that if you do inverse sine of any of those numbers between 0 and 1, you will get an acute answer. And that will be fine. The issue arises if we try to go further than pi by 2. We start repeating ourselves. You get to sine of 95 degrees, it's giving the same answer as sine of 85 degrees, for instance. And that means if you try inverse sine of whatever that value is, we're not sure if we should give an answer of 95 or 85. So that's as far as we can go to the right, but it doesn't stop us going left. And it's a good idea to go to the left, because we're not in year 11 anymore, working only with acute angles, where the principal value is sufficient because we only ever have right-angled triangles, and we can do inverse sine and not worry about the fact that there's a whole wave that we've ignored. Now we want to be able to deal with inverse sine of negative numbers. We need to be able to go back as well. So we'd consider the section between 0 and minus pi by 2. Now let's see what that looks like when we try reflecting the graph. If we take the line y equals x, we can reflect the entire sine wave, and you'll see clearly that it is now a one-to-many mapping. If you look up x equals a half, you'll find we get values at pi by 6, for instance. And if you go a bit further, we also have 5 pi by 6. And if you go down, you have something like minus 7 pi by 6, and so on and so forth. There are an unlimited number of solutions if we're going to use this graph. It's not a valid function, so we can't use it. What we do instead is restrict it. This is the reflection of just the piece that I've chosen to restrict. It goes between minus pi and pi on the original graph, and when we reflect that, we get y values between, minus pi by 2 and pi by 2. And the reflection gives y values between minus pi by 2 and pi by 2. This is the graph of y equals inverse sine x. You can do a similar thing with cos and tan. Start from the origin, see how far to the right you can go before you have a problem, and then see how far to the left you can go, and see if you can get as full a range as you can for each one. So once again, this is the inverse sine graph in red, but in black we have the restricted sine graph. It looks a bit more boring than the classic sine wave that we've come to know and love, but that's because this graph is not allowed to wobble. It can't oscillate, it can't go back and forth, because if it does, it will start repeating y values, output values. We need to know, if we have a particular output value, exactly what the input value was that produced that. Now, what we need to look at closely here to make our life easier when we're sketching these later on is specifically the endpoints of this section of the graph. We know sine waves, we know them like the back of our hands by this point, and we know the key points on them. In particular, the first maximum point happens at pi by 2, and it has a value of 1, so the coordinates are pi by 2, 1. At the other end, the first minimum as we go to the left is minus pi by 2, minus 1. Now, if we're reflecting in the line y equals x, the great thing about a reflection like that is that if you have the coordinates of a point on the graph, all you need to do to reflect that point is swap the x and y coordinates. The point pi by 2, 1 becomes the point 1 pi by 2, and the point minus pi by 2, minus 1, likewise, minus 1, minus pi by 2. The first thing I do when I'm asked to sketch a graph like this is to sketch the black graph, y equals sine x, within the restricted domain, minus 90 to 90, or minus pi by 2 to pi by 2, and then I reflect the endpoints. Once I've reflected the endpoints, and I've got a reasonably to scale graph, it's pretty easy to fill in the rest. It starts out vertical at each end, because sine x starts out horizontal at each end, and we have a reflection. So horizontal becomes vertical, vertical becomes horizontal. That will be a useful one to remember. So instead of increasing at a gradually decreasing rate, which is what sine does between 0 and pi by 2, it increases at a gradually increasing rate between 0 and 1, reaching a height of pi by 2. We can do a similar thing for cos. Cos looks in some ways similar, but in other ways quite different. And that's because if you start at the origin, or in this case start at x equals 0, you end up at the point 0, 1, you can go a long way to the right, a long way in the positive direction before you start repeating yourself. And that's why when you do inverse cos of any value, you will always get results that are positive. You don't get negative results like you do from inverse sine. What you hopefully notice when you tried a few values before, inverse sine can give you positive or negative, but always acute angles, whereas inverse cos will give you sometimes acute, sometimes obtuse, but always positive angles. If in doubt, or if you're getting mixed up and you want to double check, you can just try some numbers on the calculator and it'll convince you which way around it should be. Again, we can do a similar thing with this. We start at the beginning, we go as far as we can to the right before we start repeating ourselves, and then we find we've got enough. We've gone from 1 to minus 1. That's sufficient quantity. We can't even go to the left now because we'll immediately start repeating ourselves. So we mark on the coordinates of the points we have, 0, 1, and pi minus 1. Then you swap them. 0, 1 becomes 1, 0, pi minus 1 becomes minus 1 pi. Plot those points, join them up. Just like with sine, the cos graph starts horizontal and ends horizontal, so the inverse cos graph will start vertical and end vertical. Once you know that, you can sketch on the graph. Tan is probably the strangest one. One of the nice things about tan is that you can do inverse tan of any number you like. The reason for that is that although we have to stop at pi by 2 and at minus pi by 2, just like with sine, we stop at an asymptote in each case, which means tan isn't restricted. There's no end point on this one. Tan shoots off towards positive infinity when you get closer and closer to pi by 2, and towards negative infinity as you get closer and closer to negative pi by 2. So my graph of inverse tan can go as far as you like. You can substitute any number into it, because no matter how high up you go on the y-axis, you can move along less than pi by 2 and you will hit the tan graph. It's still possible to use the same kind of technique to draw this though. We start at the beginning, we've got the origin included. You can go as far to the right as the first asymptote, and then you better stop because you don't want to include discontinuities if you can avoid it. We could have done what cos does and have everything from 0 to pi, but then there'd be a hole in the middle. You wouldn't be able to have that 90 degrees in there. So instead, we decide to move backwards so we don't have any asymptotes, and we have the same domain for the restricted tan function as we had for the restricted sine function, between minus pi by 2 and pi by 2. When we reflect, it helps to think of endpoints. Now, in some sense, we don't have endpoints, of course, but we can safely write them in like this: minus pi by 2 minus infinity, and pi by 2 infinity. We can reflect those in the same way, and you can see that what essentially that tells me is that we have the vertical asymptotes from tan converting into horizontal asymptotes for inverse tan. The inverse tan graph will continue to increase, but at a slower and slower rate because it is approaching a hard limit at pi by 2. It will never get higher than pi by 2, no matter how large a number you put in. You can test it out. You can try doing inverse tan right now of the biggest number your calculator can plausibly hold, and what you'll find is if you make a big enough number, it'll tell you the answer is 90 degrees or pi by 2, but all it's doing is rounding. So you're getting as close as you like to pi by 2, or if you try a large negative number, as close as you like to negative pi by 2, but you never quite get there. Okay, the last thing you need to be familiar with is how to deal with the range and domain. Remember, the domain of a function is the numbers that go into it, the input values, and the range are the numbers that come out from it, the values that you get from the function. So the domain is defined in terms of x, the range is defined in terms of f of x, the function itself. And if you have an inverse function, the domain and range are switched. X and y are swapped. What was an input for the original function is now an output for the inverse function, and vice versa. So these are the key things to be aware of, and if you remember why they work, it's much easier than trying to memorize them for every single function. Inverse sine has a domain between 1 and minus 1 because that's the range of the sine function. It has a domain of between 1 and minus 1, and it has a range between minus pi by 2 and pi by 2 because the restricted sine function had a domain between minus pi by 2 and pi by 2. This is cos. The restricted cos graph includes positive, acute and obtuse angles, so anything from 0 to pi in its domain. And the range was everything between 1 and minus 1. So the domain of the inverse cos function will be between 1 and minus 1, while the range will be between 0 and pi. And finally, the tan graph has an unrestricted range, which means the inverse tan graph has an unrestricted domain. The domain of the tan graph is between minus pi by 2 and pi by 2, which looks just like sine, but there's a subtle important difference. Because tan approaches an asymptote at both pi by 2 and minus pi by 2, we can't include those points. You can't do tan of 90 or tan of minus 90, it's undefined at that point. So make sure you use strict inequality signs here. As a result, the inverse function also has strict inequality signs for the range. It cannot ever give you a value of 90 or minus 90. The calculator might think it can, but it can't.